Hi there, and welcome back to MA211. For this video we're going to be talking about calculating inverse Laplace transforms. Before I do that, I want to talk about some tools that we can use in Maple to help us out. Maple can actually calculate Laplace transforms and inverse Laplace transforms for us. Before we can do that though, we have to import the int_trans package. So you type with int_trans, hit enter, and it should tell you that you have all these commands here. These are now available to you. Once you've imported the int_trans commands, now you can ask for, say, the Laplace transform of sine of 4t. Now you have to tell it what's currently the independent variable. So t is the independent variable now, and I'd like that transformed into a function of s. So there you go, the Laplace transform of sine 4t is 4 over s squared plus 16, which you can verify if you look at your table of Laplace transforms. Maple can also calculate inverse Laplace transforms for us. Suppose I want to know the inverse Laplace transform of, say, s plus 5 over s squared plus 6. Oops. We currently have a function of s. I'd like it turned into a function of t, so I type s comma t. And Maple tells me that the inverse Laplace transform is that thing, which is correct. Okay, so Maple can calculate Laplace and inverse Laplace transforms for us. Don't forget to import the int_trans package before you try. Before we go any farther, I need you to remember about partial fraction decompositions. It's a technique from Calc 2. When you have a rational function, you can convert the rational function into a sum of simpler rational functions. Maple can go ahead and calculate partial fraction decompositions for us. I want to point out that I expect you to be able to calculate partial fraction decompositions by hand. There's a note in the book on calculating simple ones. Your Calc 2 book goes through the whole thing for you. Review that if you're not comfortable calculating partial fraction decompositions. I will certainly expect you on a quiz or an exam to be able to do this by hand. However, on your homework or whenever you don't feel like going through the rigmarole, it's okay if you use Maple to calculate them for you. It's a little bit of an involved process sometimes. I don't feel like doing it every time, so it's okay to use Maple when you don't feel like it, but you cannot use it as a crutch. You must be able to do this by hand. I will expect you to be able to do this by hand. So if I want to convert, say, something like this, s plus 2 over, suppose I have a denominator that looks like this, s plus 1 times s plus 4. I want to convert that to partial fractions, so I type parfrac here. Maple is telling me that the expression s plus 2 divided by s plus 1 times s plus 4, that's exactly the same as 1/3 times 1 over s plus 1 plus 2/3 times 1 over s plus 4. Now be careful when you use this convert to parfrac. You really need to put in the times sign between these two. If you don't put in the times sign, then Maple doesn't do anything smart. It just does that. Okay, it did nothing there. If you put in the times sign, then it does what you think it should do. Of course, you don't have to put this in factored form. If you had written down here s squared plus 5s plus 4, which is just what I had there, but it expanded out, then Maple would do the exact same thing for you. Either way is fine. Okay. So let's get to calculating some inverse Laplace transforms. Alright, calculating inverse Laplace transforms. This first problem says find the inverse Laplace transform of 1 over s squared. So what's this asking? This is asking what function has Laplace transform 1 over s squared? So there is no certain method to calculating these. You're just trying to find a function such that when you Laplace transform it, you get 1 over s squared. If you look in your table, you will see that the Laplace transform of t is indeed 1 over s squared. So that's it. That's it. So t is the inverse Laplace transform of 1 over s squared. And that's the end of the story. Okay, let's try another one. I want to calculate the inverse Laplace transform of 1 over s cubed. And if you look in your table, you won't find anything immediately that Laplace transforms to be 1 over s cubed. But if you look carefully, you'll find that the Laplace transform of t squared is 2 over s cubed. Okay? 2 over s cubed, not 2 over s squared. So what you want to do is rearrange this thing to have a 2 over s cubed in it. So let's see, the inverse Laplace transform of 1 over s cubed, well, that's the same thing as the inverse Laplace transform of 1/2 times 2 over s cubed. And now, just like the Laplace transform, the inverse Laplace transform is linear. So this is 1/2 times the inverse Laplace transform of 2 over s cubed. And now we know that the inverse Laplace transform of 2 over s cubed is t squared. So this is 1/2 t squared. Let's try another one. I want the inverse Laplace transform of s squared plus 49. Once again, you can't find anything in your table immediately that'll Laplace transform to be s squared over 49, but you can find something that'll Laplace transform to be 7 over s squared plus 49. So the thing you want to see is that the Laplace transform of sine 7t is 7 over s squared plus 49. So what am I going to do? I'm going to try and rearrange this thing to look like that thing by multiplying by a constant, because the constant can come out of the inverse Laplace transform. So the inverse Laplace transform of 5 over s squared plus 49, well, that's the same thing as the inverse Laplace transform of 5 over 7 times 7 over s squared plus 49. That's 5/7 the inverse Laplace transform of 7 over s squared plus 49. And that part, I know what that is. So that's 5/7 times sine 7t. So this is pretty common. Pretty commonly you'll have to inverse Laplace transform a thing, and it's off by a constant multiple. You'll need to multiply the thing and divide it by a constant to be able to calculate the correct inverse Laplace transform. Okay, so this one's a little bit different. Here I have a denominator that I don't really recognize. This doesn't look like the denominator for the Laplace transform of anything in the table. So what am I going to do? I'm going to use partial fractions . The partial fractions decomposition says that s plus 1 over s squared minus 4s, that's the same thing as 5/4 times 1 over s minus 4 minus 1/4 times 1 over s. Alright, so what we really have is we want to inverse Laplace transform 5/4 times 1 over s minus 4 minus 1/4 times 1 over s. That's going to be 5/4 times the inverse Laplace transform of 1 over s minus 4 minus 1/4 times the inverse Laplace transform of 1 over s. And now we can look those up in the table. The inverse Laplace transform of 1 over s minus 4 is e to the 4t. The inverse Laplace transform of 1 over s turns out to be just 1, So this is 5/4 e to the 4t minus 1/4. Okay. Here we have something slightly different. We want to inverse Laplace transform this thing. This denominator looks like s squared plus a constant, so it looks like the denominator for a sine or cosine Laplace transform. So let me just rewrite this. The thing I'm going to do is break this into two parts. I'll break off the s term, and I'll have something involving a cosine when I inverse Laplace transform. And I'll break off the one term, and I'll have something involving a sine. So here I have the inverse Laplace transform of s over s squared plus 2 plus 1 over s squared plus 2. Okay. So that's the inverse Laplace transform of s over s squared plus 2, which I know, plus the inverse Laplace transform of 1 over s squared plus 2. I'll have to fix that guy up a little bit, but I'm pretty close. So this inverse Laplace transform I can calculate immediately. This is cosine of root 2t. Plus, what I'll write is this is the inverse Laplace transform of 1 over root 2 times root 2 over s squared plus 2. Now this thing, again, comes out of the inverse Laplace transform. I'm left with the inverse Laplace transform of root 2 over s squared plus 2, and that's sine root 2t. So this turns into cosine root 2t plus 1 over root 2 times sine root 2t. So that's very common. Whenever you see a quadratic in the denominator that looks like s squared plus a constant, you should be thinking about breaking up the numerator into two parts, one that involves the s term, one that involves the constant term. Okay, and let's try this one. This one's sort of similar to one we've seen before. Here in the denominator I have a cubic. Basically, anytime you see a high degree denominator, you should be trying a partial fractions decomposition to rewrite this in terms of a sum of things whose denominators are linear and things with irreducible quadratics in there. So let's see, if I do a partial fractions decomposition, you can check that s over s plus 2 times s squared plus 4 is really equal to negative 1/4 times 1 over s plus 2 plus 1/4 times s plus 2 over s squared plus 4. So here's what I'm left with. I want the inverse Laplace transform of negative 1/4 times 1 over s plus 2. That shouldn't be any trouble to inverse Laplace transform. Plus 1/4 times s plus 2 over s squared plus 4. And that part I'll need to break into parts. I'll break off this term and I'll break off that term. But again, it shouldn't be any trouble to inverse Laplace transform. So this will be negative 1/4 inverse Laplace transform of 1 over s plus 2. Plus, this is 1/4 inverse Laplace transform of s over s squared plus 4. Plus 1/4 inverse Laplace transform of 2 over s squared plus 4. And now we can calculate this. This is negative 1/4. The inverse Laplace transform of 1 over s plus 2 is e to the negative 2t. Plus 1/4. The inverse Laplace transform of s over s plus 4 is cosine 2t. And plus 1/4. The inverse Laplace transform of 2 over s squared plus 4 is sine of 2t. And that's really about it. For now, that's all there is to calculating inverse Laplace transforms. You'll need a few tricks. You should always be trying to calculate the partial fractions decomposition of rational functions. And you might need to mess with the constants like we did up here. You might be needing to multiply and divide by a constant, and you might be needing to break fractions into two parts like we did on this problem. But other than that, these are all pretty much the same.